Here we're going to look at solving exponential equations. So there's the way we're going to look at here, where the goal is to get the same base on both sides. So it shows here to say I've like b raised to the n power equals b raised to the n power. If that's the case, we can actually cross out the base from both sides, take what the exponents are, set them equal to each other, and that'll usually give us an equation we can solve. We see that here on the first one that goes 5 raised to the 8 minus 7x equals 5 raised to the 4x minus 2. Again, we see the same base on both sides. We can cross that base out here and just write down the 8 minus 7x equal to the 4x minus 2. Now it becomes just an exercise in solving for x. I went ahead and added the 7x over to both sides here. So we can write that as 8 equals 11x minus 2. We'll add the 2 over to both sides. 10 equals 11x, or 11x equals 10. We'll divide out the 11 from both sides, and we'll write it as x is equal to 10 over 11. Next one we're going to take a look at is 5 raised to the negative 4x minus x squared equals 5 raised to the third power. Like the last one, we have the same base on both sides. We can just essentially go ahead and get rid of those bases, cross them out, and write negative 4x minus x squared is equal to 3. Now this is actually a quadratic equation, and due to the fact that it has x squared involved, we have two ways of solving. We can either solve by factoring, or we can solve by using the quadratic formula. Usually factoring is the easiest way to go if it's possible. In order to do this, or really either one of them, we need to get everything on one side of the equation. So I went ahead and added the x squared over to both sides, wrote it like negative 4x is equal to x squared plus 3. Then I went ahead and added the 4x over to both sides, writing it like 0 equals x squared plus 4x plus 3, or we could write it instead as x squared plus 4x plus 3 equal to 0. Now we're all set up for the factoring. If we look at this here and want to factor it, something in parentheses times something in parentheses. In this case, we could take a shortcut to find two numbers that multiply to 3 and add to 4. That would be 1 times 3, and 1 plus 3 is 4. So we'll write down here x plus 3 times x plus 1. Whenever we factor and solve, we take each factor and set each one equal to 0. So x plus 3 equal to 0, x plus 1 equal to 0. For plus 3, we're going to subtract the 3 from both sides and write it as x equals negative 3. For plus 1, we're going to subtract 1 from both sides, write it as x equals negative 1. Here we have e raised to the 9x plus 3 minus e equal to 0. Now this does have the same base, but we need the same base on both sides of the equation. So what I'm going to do first is add the e over to the other side and make it e raised to the 9x plus 3 is equal to e. Now we have the same base on both sides. What's the power of e when there's no power written up here? Well, that's an understood first power. So when I cross out an e from both sides, I'm going to take the 9x plus 3 and have that equal to 1. To solve from here, we're going to subtract the 3 from both sides. That'll leave us with 9x is equal to negative 2. We'll divide out the 9 from both sides. Write this as x is equal to negative 2 over 9. Here let's look at x with e raised to the negative x plus 3e raised to the negative x equal to 0. In order to solve this one, we can't actually get the same base on both sides. We actually need to recognize the fact that this e raised to the negative x is a common factor of both terms. So what I'm going to do first is I'm going to factor out the e raised to the negative x. If I do that here, it'll come out as a single e raised to the negative x, and then next to it in parentheses, I'll write x plus 3, and then that's equal to 0. Like before, if we can factor it, we can solve it by taking each factor set equal to 0. This first one here that says e raised to the negative x is equal to 0, that one is actually not solvable. Due to the fact that, especially when we went back and looked at the graphs of the exponential functions, they never made it to 0. That was not part of the domain, or not part of the range, in other words. So this type of equation where the exponential is equal to 0 cannot be solved. But we can do something with the x plus 3. We're going to subtract the 3 over and write it as x equals negative 3. And that's going to be our only solution here. Just that one number from that one part of the equation. Here's one that goes 27 raised to the x plus 3 is equal to 9 raised to the x minus 1. This one does not have the same base necessarily, but we're going to be able to get the same base on both sides because 27 and 9 have something in common. In this case, 3 raised to a power can be both 27 and 9. 3 raised to the third is 27, and 3 raised to the second is 9. So I'm going to start out by rewriting this thing as 3 raised to the third for 27, and that's raised to the x plus 3, equal to 3 squared, and that's raised to the x minus 1. Now, whenever we have the situation where exponents are next to more exponents, we multiply these exponents together. So the 3 is going to multiply to both x and 3. 2 is going to multiply like we're distributing to the x minus 1. We'll write it as 3 raised to the 3x plus 9 is equal to 3 raised to the 2x minus 2. Now we have the same base, 3. We can cross it out, leaving us with just the what's up there on top, 3x plus 9 equal to 2x minus 2. And that solves just like any equation would from here. Let's subtract the 2x over from both sides. X plus 9 is equal to negative 2. Subtract over the 9 from both sides. And as a result, we'll have x is equal to negative 11. Here we're going to talk about the topic of compound interest. And for compound interest, we have a formula that kind of works along the same lines as the exponential functions, basically. There's exponents involved. It goes a equals p, then parentheses r, or 1 plus r over m, close parenthesis, all raised to the mt power. That's for something called m compounding periods per year. Then there's something called continuous compounding. It uses a different formula, a equals pe raised to the rt power. Now what these letters stand for is listed here. P stands for the principal, also called present value. That's usually thought of as the initial amount that's invested. A stands for the amount in the future after t years have passed. So like the accumulated amount or the future value. Like it says, t is time in years, and r is the interest rate. An important thing to keep in mind about the interest rate is we need to use it as a decimal, even if it's stated as a percentage. So convert the percentage into a decimal. If we look at this first one here, where it says $6,300 is invested at a 3.1% interest rate, compounded monthly. How much will be there after 9 months or 10 years? So first off, let's identify the letters in the formula here. P is the present value or principal. That's the starting amount of $6,300. Interest rate R is the 3.1%, but as a decimal, we need to shift the decimal point 2 spaces over and write it as 0.031, and that's what we're going to use for R. Now the letter M stands for how many times interest is compounded, or in other words, paid per year. And this time it says compounded monthly, which means it's compounded 12 times a year. That means the letter M stands for 12. Now the first one for 9 months, let's talk about how we're going to do that here. For 9 months, we need to convert that into how much of the year it's working with. That means T is equal to 9 months out of 12 in the year. So that means the letter T for time is 9/12 for 9 months out of 12 in the year. And I'm using this because we're counting in years, so we have to take a fraction of the whole year if it's not a full 12 months. Now what we're going to do is to plug this all into the formula. So following with the formula above, we'll write A is equal to P, 6,300, then we'll open a parenthesis and write 1 plus R, 0.031, divided by M, which is 12, close the parenthesis. Then that's raised to a power of M, which is 12, times T, which is 9/12. This is the job for the calculator now. Here's what my calculator shows when I plugged all that in. And it came out with amount of money here at $6,447. Now we're going to round this to dollars and cents. So since we're going to round here, and the number at the end is a 7, that's going to round the 9 up to a 0. So really we need to round the next number up, so it's actually going to be $6,448 when we round it up to the nearest cent. For the next one, we're going to do 10 years, which means we just use the number 10 for the letter for T. Pretty much that means the formula is going to work out the same as what we just wrote out a second ago. So 6,300 parentheses 1 plus 0.031 divided by 12 raised to the 12, but now T is 10. So we'll say the 12 times 10 power. And again, here's what my calculator gave me for this one. We're going to round it again. Now notice though, we're going to round with the number 5 here. So that's going to round this up to 0.15 at the end. For dollars and cents, we'll write this as $8,586.15. This example speaks to using compounded continuously interest. In a case like that, we use again a different formula. A equals PE raised to the RT power, where P is the initial amount, which they say the investment's $20,000. T is time, so that's the 12 years. The interest rate is given over here at 4.95%, which again, we have to convert that to a decimal. So we need to move the decimal place over 2 spaces, and we'll write this as 0.0495 for the letter R. And if we plug this into the formula, it would go 20,000 E raised to the 0.0495 times 12. We can plug this in the calculator. Well, it does have a function for E, so if we plug that in, round it off to the nearest cent, it'll come out to be $36,224.38.